Robot Talk is the podcast that sits down with robot enthusiasts from around the world and asks them the questions you always wanted answered. Like, can the robot be tailored to the user? And how does that thing work? Hello everyone! Welcome to Robot Talk. I'm your host, Claire Asher, and this week we're returning to the topic of assistive robots and finding out more about how robotics can help support people with illness and disability live more active, independent lives. Before we get started, please remember to like or rate this episode and leave us a review if that's something you can do on the platform you're listening on. And don't forget to share the podcast on social media or tell your friends about it. It really helps us reach more listeners, so thank you in advance. So, without further ado, I'm excited to introduce this week's guest. I recently had a really interesting chat with Virginia Ruiz Garate from Mondragon University, all about assistive robotics, mobility, and bio-inspired control. Today, I'm talking to Virginia Ruiz Garate, a lecturer and researcher at Mondragon University in Spain, researching bio-inspired adaptive controllers for assistive robotics. Hi, Virginia. Welcome to Robot Talk.
Hello, Claire. Thank you very much for inviting me over.
So, to get started, for your PhD research, you worked on lower limb exoskeletons as part of the CyberLegs project, where you were developing a bio-inspired control system that is more intuitive to use. So what were some of the biggest challenges that you faced in this project?
Well, I have to say there were several big challenges along this project. The main one was, of course, the purpose of the PhD itself. That was to develop those adaptive controllers for the exoskeleton that would make it intuitive to use. So the idea was to find a way to mimic the way that humans, we control the way that we walk, so that the exoskeleton will behave in a similar way and the person will feel is intuitive to use. But that means not only that you have a controller that adapts to each person, but also that adapts to the way the person is evolving over time. So that was one of the main challenges. That was the purpose of the PhD itself. But while working on it, it was a big European project in which each of the universities and research partners were doing our bit. We were doing the control part, but at the same time, our colleagues in Italy were doing the hardware. They were building the exoskeleton. Our colleagues in Ljubljana were doing the sensing and allowing us to read the signals. So putting all of that together was a big, big challenge. I spent a good couple of months developing a controller, thinking that the sensors will work in one way. Then we went and tried it. It didn't work that way. And it was all, let's start over again and rethink this. But it was a very nice collaboration and we worked very closely. We did a lot of trips and did a lot of integration marathons, to say so. And that allowed us to have a very nice final setup. And I think one of the challenges as well was the fact that when you work with assistive robots, you work with humans, and humans are unpredictable, and we learn as we go. So one of the things I found extremely surprising during this project was that we were building these exoskeletons to try and help people reduce their effort while walking or doing whatever they need to do. And at the beginning, you could see that effort reduced, but after some time, it was not so evident. And we were wondering why, until you start talking with physicians and doctors, and you realize that humans, we are indeed very adaptive. So what we do is to find the best way to utilize whatever tool we have and reduce the effort. So even if you are giving them a very bad system, they will find a way to use it and reduce the effort in order to use it. And so measuring the effort was not as straightforward as we thought it was, because people would just find a way to reduce the effort anyway.
Yeah. That's really interesting. Yeah. So tell me a bit more about the control system you developed. I mean, the most intuitive thing is to use my brain, but I'm assuming we're not talking like brain computer interface here. So
No.
tell me how it works.
So we tried to start from the brain indeed, but the theory on how we use our cyclic movements, how we perform things like walking or repetitive tasks, is we have something called motor primitives and central pattern generators, everything which is encoded on our spinal cord.
Okay.
So our brain sends a signal to the spinal cord that says it's time to activate this. And then the spinal cord starts working like a sort of clock, giving you the time and the
Mm,
pace. And there is sort of bucket signals stored there that they go out as the clock is ticking,
right. Okay.
and they go to the muscles and they activate the muscles in a rhythmic way. Because you have to think that we have dozens of muscles in our body. And if our brain was in charge of controlling all of them and synchronizing them so nothing happens, it would be
Mm,
quite overloading. So the brain is kind of only on control of the higher inputs or outputs in this case, while the spinal cord has all the signals encoded inside that needs to go to the muscles. And that's what we try to recreate. So our colleagues in Ljubljana did an intention detection algorithm that act as the brain, saying, well, I
mm.
want to walk, or I want to go upstairs or downstairs. And then we recreated in my PhD the whole system of central pattern generators that act as the clock, and the motor primitives that are those basic signals then get output to the muscles. We built a virtual musculoskeletal system of the body, and we got all these signals, bring them to this virtual system, and then generate the torques from there that were sent to the exoskeleton. So the things that we were reading from the human were indeed not brain signals. We were reading kinematics, we were reading joint angles and ground
Mm.
reaction forces. So from that feed-forward system that we developed based on the biological principles, we mix that with the actual position of the person. So how the user was indeed moving at that particular time. And the mix of those two things into the virtual human model gave us those torques that were adapted and were compliant to the way that the person was moving.
Wow, that's really cool. Yeah, it's so interesting to kind of combine, how the biological system works with like this kind of engineering approach. Pairing those two different sciences together is cool.
Yeah, yeah, it was a discovery for me. I when I studied robotics, I didn't know you could mix it with biology.
Yeah.
And as I went on in my master, I saw that it was possible and found it very interesting. So I wanted to go deeper on that, and here we are.
Yeah. So, a project that you recently worked on was an adaptive home assistance robot for people who've suffered from a stroke.
Mhm.
So, can you tell me a bit more about that project?
Yes, so that project stemmed from a previous project that was being done in the laboratory where I was working in Bristol. And they had
Mm.
developed a robotic system to help people do the movement from sit to a stand and from a stand to sit. And we realized, well, that's crucial because most of the studies, they worry about walking for people with impairments. But to
Mm.
start working, first you need to stand up from your chair.
Yeah.
And when you finish, you need to sit down. So, with kind of the same ideas in the PhD, what we did in this work was to record people doing several sit to stand movements. And we recorded more than 10 healthy people and around 7 people who had suffered a stroke and had
Mm.
different levels of stroke. All of them were able to sit and stand on their own, but they had very different patterns of doing so.
Mm.
And with this information, what we did was first to compare it and see the difference between healthy patterns and people who have suffered stroke and how they differ, and then try to build a predictive system that would somehow tell me from the parameters of a person, height and weight, what would be a sort of standard way to stand up in an ideal scenario if they didn't have suffer a stroke. So if I have a patient that has suffered a stroke, with this prediction algorithm, I would know their trajectory for sitting down or standing up as if they had not suffered the stroke. In that way, if I build a robotic system like the one they had in the laboratory, I can control it to drive the person to an ideal pattern. We never talk about having them forced to do a movement, but always kind of guiding them towards that movement.
Okay. And so was that robot kind of an exoskeleton type structure?
In that case, it was an external kind of moving chair,
Okay.
like one of these walkers, but it was hanging from the roof of the house and was pulling you up.
Yeah. I mean, I think, yeah, what you were saying about guiding rather than sort of forcing people is really important. It brings to mind, I don't know if you've ever watched any of the Wallace and Gromit movies, but there's the classic one of the wrong trousers where he has these robotic kind of trousers that go haywire and he's being sort of, carried around town. Yeah, that's very funny in a cartoon, but not obviously what we want in reality.
Exactly. Yeah, that's very important because sometimes every person walks, moves, and acts in a different way, and forcing someone into a different pattern might be of help at the beginning if they cannot move at all, but afterwards you might end up even injuring them. So you have to be careful with forcing movement.
Yeah, definitely. And yeah, I mean, every stroke is kind of sort of unique in the sense that it's going to have slightly different effects on the person, and obviously the person was unique to start with, which kind of leads me into something I wanted to discuss with you more generally, like how much do these kinds of assistive technologies need to be tailored to the specifics of the individual and their disability or physical restriction, or to what extent can you kind of make them a bit more general purpose?
Well, I think for small solutions, you can be more generic. I'm thinking even having a sort of long stick with a gripper that anyone can use to reach farther. And you can have small solutions like that are very generic. But like you were saying, every disability is different. So we're not only talking about different types of disability that, of course, need different solutions, but also within a stroke, for example, every person reacts and has a different impact in their daily living. So, for example, with the stroke people that we were recording, some of them, I remember one in particular, the measurements were even better than for a healthy person. So we're like, okay, not much needed here, I guess.
Yeah.
But some other people that might look healthier at the first sight and they had very deviated patterns from the ideal ones. So even within the same impairment, it affects people very differently. That's why usually you need a human physiotherapist to do something specific to your situation. And even if you have the same type of a stroke at the same level and everything, like you say, every human is different. You have different preferences, you have different aches, you have different feelings. So even things like just adapting to your mood, like if you're down and you don't want to exercise or you don't want to be pushed around, or today I feel more active and more energetic and I really want to move forward. So the system should be able to adapt to that. I was thinking of an example, and one of them is, for example, our cars. We have cars that we try to customize as much as possible. And even if we have a standard car, when you sit on the chair of your car, you tune the chair. You lift the
Yeah.
bag, you move the seat a bit forward, even you move the driving wheel forward and backwards. So we need some level of adaptation always. And people who have impairment, they also have their own challenges that make everyday tasks that are not, the environment is not built for them. So it's more challenging, and adding difficulty to that challenge, that's, I think it's not very nice. So it's better if we try
Mm.
to make that interface with the environment as easy as possible for them, so we can reduce the difficulty they have into interacting with this non-adapted environment. And also there is, if you see the rates of that people give up the assistive technologies is huge. There are
Mm.
papers and research on this where you see tables of people who have been given assistive technology. They use it for a week and then to just give up, because a bit like
Yeah.
Wallace and Gromit is taking them where they don't want to be. And some of them don't even try it
Mm.
because it's too complicated, too many setups, and I can't be bothered. Um, I also remember a funny example from one of the first conference I went to as a student. It was a biorobotics conference or wearable robotics conference,
Yeah.
and there was a panel of speakers, very professors and important people talking there, and one of them was an amputee, and you would think that he was wearing the latest technology, and instead he was wearing a hook for the hand. And I mean, I was surrounded by robots and wearables
Yeah.
and things, and he was like, this is very easy to use, it's very manageable, it always does what I want, it's
Mm.
predictable, and it's plug and play, I just put it on and it works. So
Yeah.
that got me thinking, well, I mean, this person is in this world. He knows about the technology, he knows everything, and instead he still chooses to use a simple hook.
Yeah.
So we do need to simplify this technology and really make it adapted to these people, because one of the things, for example, hooks or passive systems, they call them, is that they move as the person moves. So some of them have straps on the shoulder, and as the person moves the shoulder, the assistive device will, for example, open or close a hand depending on how much they moved. So there is a
Mm.
direct connection between what they want to do and how the device is moving, and it's intuitive for them. And we need to replicate this intuitiveness and adaptiveness into more complex systems.
Yeah. Yeah. Absolutely. And I guess this kind of underscores the importance of consulting, potential users of the technology right from the start of the
Yeah.
design process.
Yeah. This is something that is now, I would say, very trendy, but is very important. That is to bring participants from the beginning into the discussions. Um, of course, you need something, some context to give them. But in most projects now, there is always an element of focus groups
Mm.
or discussions, interviews with final end users. And in some of the works that we are developing now, for example, we are developing systems for people with tetraplegia, and we are planning on some focus groups together with some home places where they stay to
Mm.
know their needs, and also let them see the system and tune it or give suggestions as they would like it to be. And this user-centric design, that is the word that
Yeah.
is now an element everywhere. I think it's vital, and until now it was very disregarded. I think was a big part of the problem was that us engineers were buying very cool technology
Yeah.
without the user into consideration. So then the user would take and say, "What is this?" So I remember a couple of years ago, we ran a workshop at IRIM in Italy on assistive technologies.
Mm.
And I think it was called something like Assistive Technologies, What Are We Missing?
Okay.
And we brought us some end users, and there was a design engineer, Maria Fossati, who was a user of a hand, and she works in the design of the hand. And one of the things she said was that the first time she went into the lab and they told her, this is the hand we want you to redesign and to think, you have to wear it for a couple of days. And she saw the hand and say, hell no, I'm not wearing that. It's part of my body.
Yeah.
So I'm embedding that into my body. I don't want to feel like a robot or something ugly. I want something pretty. And there are also very nice companies now that do all these prostheses with superhero things for kids, so they will feel enthusiastic about wearing them. I think that's a pretty good change of perspective into the whole robotic prosthetic world.
Yeah, definitely. I mean, aesthetics is probably not something you think of if you're not a user of that product.
Exactly.
So, what do you think the future holds for the field of assistive robotics?
Well, I think it's very bright, but of course, I'm an optimistic in that sense. I think we are going to see more and more implants, things that maybe at the beginning we don't see so much as robotic, but things like the implants, they already exist for hearing, or they're going to be developing for eyesight as well. And more wearables. Now it's more common to see people with some level of automation in their prostheses, even, especially for leg prostheses. Some of them passive, but some of them start to be active, and you can see people on the street wearing them. And also one thing I like is that people are starting to be less ashamed of having them, and they are owning them and being proud of what they are. And that is also a big boost in the technology, because if you don't have that restriction of trying to hide it, then you can move forward a lot faster. And I really hope that people will start using them more. And what I'm looking forward is also for governments to start supporting these technologies, because one of the main barriers is the cost of these technologies. And most people have to rely on charities to be able to buy them. And I think it's essential for a person to feel full again. It does not need to be a prosthetic or an orthosis that makes you be like you were before, but maybe something that you feel good with, and you can be active in society as well. So I think it's a win for the person, but it's also a win for the society itself, because that person is back into it. And also, apart from orthosis and prosthetics, we can also think about all those assistive robots that we can have at home, like, let's say, Wilt Alexa, or any robot that will help you do little things at home and are going to liberate us from a lot of dual and dirty tasks that we have to do, and we can have more time to enjoy.
Yeah, absolutely. It makes me think of, there's a quote that I will not get right, but it's words to the effect of, once technology becomes embedded in our lives, if we cease to see it as technology anymore, it's just there. It's just part of the environment.
Yeah, I think we have to see them as tools. People are sometimes afraid of robots because they see them as peers, but they are not. They are like the scissors in your kitchen, or the knife, or the spoon.
Yeah.
You use it for a purpose, and where not, you put it back on the closet, and that's it.
Yeah.
I mean, it's a tool to make our lives easier, and that's how we should use it.
Yeah, definitely. You also made me think of, when you were talking about the kind of availability of some of these robotic tools and the cost of them. Obviously, if governments can support people to get them, that would be great. I'm also thinking about kind of accessibility for people who live in developing nations. I guess there's always a trade-off between creating something that is the latest state-of-the-art technology versus something that's a bit cheaper and can be available to more people.
Yeah, I know there are several startups that are focusing on low-cost prosthetics and orthoses. Of course, in this case, they are more generic, but many of them are customizable, and especially now with the 3D printers, it's quite easy to get something customized, at least in size and shape. I think there is a very cool project for 3D printing plastic hands for kids.
Okay.
So, yeah, there is a lot of effort in there. And I always think that when you push technology forward, somehow the lower levels of technology get cheaper.
Yeah.
So I hope, it's not only about the materials, but also the technology gets, and the know-how gets cheaper somehow. And yeah, I hope that's a reality soon, that the prices will get lower. But again, it's better to have low-cost devices that are available for everyone. But again, if that device is painful to use, it's very difficult to use, it's useless.
Yeah, exactly. Virginia, it's been lovely chatting to you today. I've been speaking to Virginia Ruiz Garate, a lecturer and researcher at Mondragon University. Thank you.
Thank you very much, Claire.
Thanks for listening. If you enjoy Robot Talk, I'd really appreciate it if you could share the podcast and leave a review to let us know what you think. And if you've got a question you'd like me to ask one of my future guests, you can contact us on social media at Robot Talk Pod or visit robottalk.org. We regularly announce upcoming guests, and I'd love to include your robotics questions, whether they're super basic, a bit silly, or even quite profound, in my next interview. Next week, I'll be chatting to Rafael Lopez from Robotic Automation, all about mobile robots, logistics, and inspection. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk is brought to you by the Hamlin Centre, Imperial College London.